So here's the outline of what I will do. First, I will give some introduction and motivation for what I will talk about, which comes from dualities and also the related idea of quasi-dualities. And then I will give the main proposal and the conclusion. And this builds on, in this book that we wrote with Jeremy Butterfield on the philosophy of physics of duality, which actually can be downloaded as a PDF from the publisher's website. And also on a recent paper that I published, which is forthcoming in Synthase. And actually also some forthcoming work with Enrico on the case of T-duality. But let's start with the introduction and motivation. So from the philosophical side, I'm not sure where I should start. Yes, people, can you hear?
We used to have one here.
Nice.
Oh, yes.
That's fine. Works. Sorry. Okay. So from the philosophical, the part of the motivation is actually from the philosophy literature, where many of you might be aware that there has been a recent discussion revived by people by Halvorson and other people on how we should formulate scientific theories. So one of the traditional answers to that is what goes by the name of the semantic view of theories, which is to look at solutions or philosophers call them models of a theory, which in philosophy of physics we often think of as solution spaces of the equations. And so the standard line on this semantic view is that a theory is a collection of models that satisfy some appropriate set of equations. Or dynamical conditions. Now, various authors have argued, in the context especially of theoretical equivalence, when they ask about when are two theories equivalent to each other, they have argued that this traditional view is insufficient because just a set of models is not enough. There is structure on this set of models. And the motivation for that has come from various places. So Halvorson comes more from a logic perspective. However, it is fair to say that this literature leaves some open questions. In particular, what is the physical interpretation of this structure, and what structure should be considered in the first place? So my approach will be to engage with two key notions from recent physics or less recent physics, namely dualities and their generalizations, quasi-dualities, and also the notion of a moduli space, which for us will be a space of parameters on which states and quantities are the states and the quantities of our theory may depend. And this is a notion that hasn't gotten a lot of attention in the philosophy literature so far. I mean, the previous talk this morning actually displayed, talked about moduli spaces, but otherwise I think there are very few examples where moduli spaces are put to do any philosophical work. So I hope part of what I hope to do is to give you some motivation for also why moduli spaces are an interesting philosophical topic. So a sketch of the core proposal is that a physical theory is a single geometric object, and I will say more about this. So that will be the core proposal that I will discuss. And motivation from that, as I said, comes from physics, because this is a way of thinking in physics that is very pervasive, where spaces of solutions are routinely used in quantum field theory and in string theory. For example, to discuss non-perturbative aspects of quantum field theory, such as solitons, also in supersymmetric gauge theories, in quantum cosmology, in string compactification, so various places in string theory also with dualities. From philosophy, like I said, there is an all interplays between space-time and geometry. So we will get these moduli spaces, and then a natural question is, well, how to interpret these spaces. And also for the structure of scientific theories, as I said at the beginning. So we need, it seems that we need a generalization of the usual semantic view. And this also calls questions about intertheoretic relations. So how relations like theoretical equivalence, but also relations of reduction and emergence, which I won't focus on a lot today, but I will say something about it, and it's surely part of the motivation. So then, with that motivation in mind, I will give a brief overview of dualities and quasi-dualities, give you some examples and a schema for them. So, but first, recalling the recent philosophical discussion of dualities, there has been quite some work in recent years on dualities in physics. One main question that people have asked is how to interpret dualities. Do they give us cases of theories that are the same, that describe the same physical system, or are these cases of different physical systems or something in between? Or is it a case thing that we need to decide on a case-by-case basis? Another question that has been asked is about underdetermination. So do duals actually give us cases where we have empirical equivalent theories that are otherwise theoretically inequivalent, that their ontologies are really different, and does that give us a good example of underdetermination? Because so far, really good examples of underdetermination have been lacking. So this might give a good example of that. So there has been a lot of work on that. Also, common core theories. Is there a structure shared by duals that on the one hand expresses what these duals have in common, but also that maybe help us understand the duals, maybe point towards a further theoretical structure beyond. And I think we can say that there is a growing consensus of the importance of distinguishing, in the face of these questions, to distinguish, on the one hand, the formalism of theory, and on the other hand, its interpretation. So many of these questions, of course, use the formal aspect of the theory that is certainly crucial to take into account, but they are mostly about the interpretation of the theories and how that interplays with the duality. So therefore, authors have distinguished usually two parts to, for example, the question of theoretical equivalence, where two theories or models are formally equivalent according to some criterion of equivalence, and whether they have the same interpretation. And not only in the context of dualities, but more broadly. And I stress this, even though it may sound like a very basic distinction, but it hasn't always been actually made in the literature on theoretical equivalence. So in philosophical literature on theoretical equivalence, a lot of the discussion has been on the formal side and not so much on the interpretative side. And what dualities illustrate is that to discuss these questions, we really need to look at the interpretations of these theories. And people like Reed and Müller-Nielsen have developed further notions in this context, like the distinction between motivationalism and interpretationalism, which I will actually not go into further. So that's a bit of the background of the philosophical discussion, why philosophers have been interested in this and what kind of philosophical questions this goes. And to give you some examples of dualities in physics, I think for this audience, I don't really need to go through the details of these examples that are well known. So electric-magnetic duality, where we exchange basically the electric and the magnetic field in the Maxwell equations, and they remain invariant under that change. Another one is position versus momentum representations in quantum mechanics related through the Fourier transformation. Another interesting example that has been studied actually less or discussed less in the philosophical literature is Kramer-Vanier duality of the Ising model in 2 dimensions for various types of lattices. Here I have the simplest case, just the square lattice. where the Hamiltonian consists of the pairwise and nearest neighbors interactions between the spins, and then the partition function can be written in the usual way as the sum of the Boltzmann weights, and then it turns out that the partition functions of two dual Ising modes are the same up to this state-independent factor, where the temperatures and the couplings are related of the original mole and of the dual mole are related in this way. So you can see that, so beta is the coupling divided by kT, so you can see that this relation relates low temperature to high temperature. So in that sense, it is a surprising duality. It was used by Cameras and Vanier to find the value of the critical point, and it was used by Onsager to solve the two-dimensional Ising mole. Now, this can be generalized to spin dislocation duality, where we calculate not just the partition function, but also other objects, for example, the two-point correlation function between sites, and that turns out to be dual to the partition function on dual lattice with a topological defect. So that's an interesting example of a duality, and I think a lot of the physics has been also inspired by this type of example. Another example is the Sine-Gordon Thiering duality, again in 2 dimensions, where we have the Sine-Gordon mole, which is a bosonic field theory with a particular potential, this cosine potential here. It has a conserved current, which is not a Noether charge for any symmetry, but that is trivially satisfied simply by the anti-symmetry of the epsilon tensor. And on the other side of the duality, we have a Thiering, which is a fermion with this quartic interaction, and it has a global U1 current and an associated Noether current for that U1 current. And here's the dictionary between the two. So psi goes to e to the I phi, and here it is actually, for this relation, it is important that this operator is normally ordered. And also in the other direction, you can get the photon from the fermion bilinears, and the couplings of the two theories are related in this way. So in this case, the duality, again, quite surprising, it exchanges the two currents, the Noether current of this model with this other current of the bosonic model. Okay, so those are some of the examples of exact dualities that we have, where there's fairly good control over the two models.
Is it also a strong weak?
Yeah. So here, for example, if T is large, then beta will go to 0. Yes. So to introduce our jargon for dualities, so for us, a Baire theory is, so we will say that the Baire theory is realized or is modeled in different ways. So we have the models are representations of this Baire theory. You can think, for example, of the Hilbert space, description of quantum mechanics with Hilbert space and operators on it, and so that's like the Baire theory. And then you have the two representations where you choose either position representation or momentum representation, which are the two duals. So these Baire models are in general not isomorphic, so we can use this more generally also for cases that we don't have duality. They differ in their specific structure, like in equivalent representations of a group, but we will say that when the models are isomorphic, then we have a duality. Now, of course, the word model in philosophy of physics and philosophy of science has a lot of connotations, which we actually, so like specific solution, what I said at the beginning, also as an approximation or being part of a physical world as against being, some theoretical structure. We will, in our use of model, we reject these three connotations. So what we call models is really just these representations of the Baire theory, even though we can get some of these in concrete examples, we can get some of these more usual meanings of model back, but this is not what we mean by model, rather it's this one here. Now, dualities are surprising, as we have seen from, for example, bosonization, where we have a bosonic model being related to a fermionic model, so that even the statistics change. And so normally we discover a duality not in the context of working with the Baire theory, but rather working with some models that are already interpreted, as, for example, being bosonic or being fermionic. But that is really more of part of interpreting the specific structure of the model in a certain way. Another example of that, of a surprising duality, is of course ADS-CFT, where depending on how we interpret the model, we have a 5-dimensional supergravity theory or string theory in some background, or a conformal field theory in 4-dimension, 1-dimension lower. So in this way, dualities can be surprising. Now, to introduce some more jargon and notation, which nevertheless I won't use a lot, but it will return at some point, is that, so we will think of these models, I will note them by capital M, and what I call the specific structure, I will denote it by M bar. So I will write the model as, well, a representation of the theory and then the specific structure. And the main thing will be that we'll think of a Baire theory as a triple, so described by a set of states, a set of quantities, and the dynamics. So the set of states could be a Hilbert space or a phase space. Set of quantities will typically be an algebra in the case of quantum theories. And the models will themselves also be formulated as triples in this sense. So they will be representations of this Baire theory. Now then, with this notation, we can think of a duality as an isomorphism of such models, formulated, so M1 a little, M1 a little, M2, and this requires an isomorphism of the state spaces and an isomorphism of the quantities. Now, if these state spaces usually come with structures, so that means that this, for example, symmetries, that means that those structures also need to be preserved by the isomorphism. And the isomorphism is such that the values of the quantities match. So all the quantities that we calculate on either side of the model, their numerical values should be the same as the condition you see here. And also that it is equivalent for the two triples dynamics. So there is basically a commuting map. If you think of the dynamics as being, let's say, time evolution, for example, on your state space, then that time evolution should form a commuting diagram with the duality map. So I will write the isomorphism then in this way. So that's a bit of the jargon and the notation, what we mean by a duality, and that's fairly standard notion in the physics literature. Now, some themes that are associated with dualities. We have already seen them, hard, easy themes. So, as was already mentioned, so we have a situation of weak coupling being related to a situation at strong coupling and vice versa. So, a problem that is hard to formulate in one dual is easy to formulate in the other dual. So that's part of why dualities are really very, very useful for physicists, because it allows them to do calculations that they would otherwise not be able to do. Related theme is elementary composite. So sometimes it turns out that what is composite in one dual, for example, an operator, and we have seen this in this exponential, so this or this actually the fermionic bilinear, that's a composite operator, it gets mapped to a single boson. And there are more examples like this, where you have, let's say, a product of operators that is being mapped to an elementary operator in the other model. So an elementary field being mapped to a composite field. Also unification. So core part of the motivation for dualities in string theory is also or the study of dualities in string theory is that they point towards unifying these theories into maybe an underlying theoretical structure that connects the different limits. So that has been part of the motivation for the M theory program. Symmetry breaking, and of course we don't know whether there's such a thing as M theory, but it certainly has motivated the search for such descriptions. Symmetry breaking, connecting different vacua. This is also part of the behavior that you see in the ICML, where a low temperature phase is related to a high temperature phase, where actually there is a phase transition between the two phases. So there's a critical temperature in between. And so that's, again, a very surprising case. And then the last one, which will be important for us, is the theme of being a duality. So for me, the word duality will always, by definition, be an exact duality. So if something is not an exact duality, then it's not. Then I don't call it a duality. It's just a matter of defining the terms. If it is only an approximate duality, then I call it an effective duality. More generally, a quasi-duality. So a quasi-duality is any map between models that is close to being a duality, but that fails for being a duality either by failing to be a bijection or by failing to preserve the structure. So the quasi-duality is kind of an umbrella term for that. And I will say more about that later. Now, one salient type of duality is where you have a duality at the quantum level, where the classical models before quantization are not duals. And for example, ADS-50 is, if it is a duality, is believed to be a case of that, where we have, on the one hand, supergravity theory that, or some whose classical variables are really not the same as the elementary variables of the Yang-Mills theory on the dual boundary. So the limits where those two theories are classical are very different. It's only after you quantize it that you realize that those two theories are dual. And one way to think about this is that these are like two different semi-classical limits of this of the CFT, let's say. Okay. Yeah, so to say a bit more about quasi-duality. So that will be my umbrella term, as I said, for almost a duality. Here are some examples of it, standard examples like personalization in 3 and 4 space-time dimensions. So I said the personalization is a duality in 2 dimensions, but not in higher dimensions. So there you can get sometimes that there are theories that go to the same infrared point, but they are different in the ultraviolet. Electric magnetic duality for quantum field theory. So in the simplest examples, like the Maxwell theory in a vacuum, then this is a duality, but in more complicated examples, this is not a duality. And the other one is string theory, where, well, there is no non-perturbative formulation currently of string theory. And I would say, I don't know if Marco agrees with this, I would say that there is it's not yet known which relations are dualities or quasi-dualities. For example, whether S-duality really is a duality or whether it's something approximate. I think these are questions, and especially also these are questions that are still, in my view, not answered, even though there is evidence that at least some of these dualities may be dualities, at least in a limit. For example, T-duality, S-duality, and ADS-50 are believed to be dualities in some limits. But I think it is fair to say that that we are far from an answer to these questions. Okay, so then I move on then to the third part about the geometric view of theory, what I call the geometric view of theories. And like I said at the beginning, what I'm doing here is putting some concepts that are well studied in physics in a more philosophical context, and trying to do some philosophical work with them. So just as dualities can be used to formulate a common core theory behind the duals, quasi-dualities are often used or often believed to be useful to formulate some underlying theory, some successor theory that goes beyond the dual. So often the idea is that, for example, in the case of, let's say, the case of M theory, well, 11-dimensional supergravity and type 2A string theory, those are close to each other at a small radius of the 11th dimension, but they differ at large radius, so at strong string coupling. And so the idea there was, part of the motivation there is that this might, by using 11-dimensional supergravity, one might be able to find such a successor theory. Now, this geometric view is a view about the relation between this more comprehensive theory and its models. So what I mean by a comprehensive theory is not necessarily a non-perturbative theory or a deeper theory. It's simply, and I will say more about this, it's simply a theory that encompasses these approximate models into a larger structure, and I will give examples of these. So the claim is not that there is a single type of geometric object that across all physics is what we call a theory, because physical theories are very heterogeneous, and so there are theories with a finite or with an infinite number of degrees of freedom. But rather, the proposal has two parts. The first part is a general proposal that a physical theory is a single structured object, so a set of models with topological and geometric structure on it, and this general part will not be my focus today. Rather, we'll focus on the more specific proposal that there is a natural structure for formulating theories in cases where we have dualities and quasi-dualities, namely what I will call a model bundle. What do I mean by a model bundle? Or in which way are we to think of a model bundle? So it's a models proposal. It is a schematic proposal and not a detailed mathematical theory. So my aim here is not to in this talk is not to develop a rigorous framework for dualities. Rather, it is to be fleshed out in examples from the physics literature, also admitting that a certain amount of idealization might be involved depending on the examples. Now, having said that, it is useful to have a general way to think about theories formulated in this way. If we, for example, think of dualities, where it has been indeed useful to have these definitions, these distinctions between common core and models, which are dual models, which are representations, they have been very useful, and models in terms of triples and so on, for making more precise philosophical discussions about, for example, under determination, theoretical equivalence. So in the same sort of way, it can be useful to have such a mathematical structure that covers a broad range of examples. So it will help us to address questions about interpretation, scientific realism, and so on. Now, having said that, there is an important class of examples where mathematicians have actually worked on this. That is the Kodaira and Spencer theory of complex manifolds and complex structure deformations. Again, I will not go into this, but just to flag that it is something that mathematicians have thought about in that process. So to then say what this structure is, there are two steps. The first step is what I said at the beginning, we lift our talk of models and theories one level up. So what are normally thought of theories are now models. So we consider a set of models if each of them with a state space as a set of quantities and another. So I already said that earlier. Now, said that these models would be related together in a structure. So that is the second step. So the second step is to take into account a moduli space. So a model defined as a triple is going to depend on a set of parameters that I collectively denote by t. So I will write m of t, and these parameters are usually vacuum expectation values of operators. They could also be coupling constants. These parameters form a space with some structure. It is the moduli space. A very well-known example of a moduli space is the moduli space of complex structures of the two torus, which is this gray area here. So we have the upper half plane and the complex plane, and the complex modulus defines the cycles of the torus through this identification. So Z is a number of the complex plane, and we identify numbers that are defined in this way, and this basically gives us the complex structure basically gives us the relation between the A and the B cycles, between the short and the long cycles of the torus. So each point in this gray area defines a class of tori that have all the same shape, the same ratio between those cycles. This moduli space usually comes equipped with other structures, especially a topology, a metric, and a complex structure. Yeah, so that's the okay. So that's the notion of a moduli space. These models, and the main thing to remember is that these models are going to depend on these moduli denoted by t. Now, since the models depend on t, it is natural to think of them as functions over this base here, where the base is the moduli space. However, since the topology is often non-trivial, we need a more general structure. So we need a fiber bundle over the moduli space, where the moduli space is the base of the model bundle. The local fiber is a set of quasi-dual models, M of t, and the quasi-duality group. So I'm assuming that there is that these are quasi-dual models. So there's a quasi-duality group acting on them, acts vertically on the fibers. Okay? So then the proposal is that a physical theory is a model bundle, is a family of such models defined over a moduli space. Now, this proposal can be illustrated for the electromagnetic duality and in this what is called the Seiberg-Witten theory, where the model bundle is a vector bundle. I will say more about that example in a moment, but maybe to relate about what we know about fiber bundle, I mean what people are more familiar with from fiber bundles in physics, where they are actually used very often is of course the context of principal bundles. Where the typical fiber is homomorphic to G, to the structure group. Now, model bundles are in general not principal bundles because the fiber is in general not homomorphic to the gauge group. For example, the example I will discuss, it will be a vector space. So these quasi-dualities above a point are interpreted as transition functions. So they take us from one point in the fiber to another. There are different ways to choose the coordinates of the bundle. Now, if the transition functions are globally defined, then we recover the case of a duality. The duality is basically that in this case here is valid over the whole moduli space for all values of the parameter. Now, the usual semantic conception doesn't envisage such generalizations. So a generalization of that view is required but we do recover the semantic conception as the trivial model bundle, which is globally the product of the base and the fiber. So where we just have the base and the fiber, and even just one single point on the fiber. That would be the usual semantic. Some comments on the interpretation of these model bundles. So, in a way, this model bundle generalizes the idea of a common core to the case of quasi-dualities. It is a common core that is obtained not by reduction, but by what I call augmentation, which is analogous to there's a parallel discussion in the literature on symmetries between reduction and sophistication. So it is like sophistication about symmetry. So remember that in reduction, when we have a symmetry, the idea of reduction is to basically just reduce your phase space to just the invariant families of solutions, to remove all the specific structure from your models. That is not what we do here. Rather, it is like sophistication, where we actually include all our quasi-dual models into this bundle, and then have the isomorphisms act as the structure group in the fibers. So we keep all the information, but then relate the fibers in a particular way. A model bundle is a formal structure, so it is an aid, not a substitute for substantive interpretive discussions of scientific realism and theoretical equivalence, and so on. So we have, for example, we want to discuss theoretical equivalence, and we have the usual interpretive requirements here. Also, I'm not defending a direct realism, so there's a parallel discussion about realism, about such structures in philosophy of science, but I'm not defending that one should be a realist about this model bundle. Rather, my position is a cautious realism, where a substantive semantic analysis needs to be done before we can be realist about a model bundle. That means that we need to look at these model bundles on a case-by-case basis and first figure out what is their physical interpretation. Now, having said that, obviously, the formalism is substantive. So saying that a theory, rather than being just a collection of models, is a collection of models with some structure on them, is a substantive move. So it is bound to have some implications for ontological questions about scientific theories. Now, to give some examples where these structures have appeared in physics and philosophy before. So actually, after I wrote the paper, I was reminded of these examples worked out by Klaas Landsman and also Feinzeig on C-star algebras. Basically, they study the classical limit of quantum mechanics. And so they think of H bar as a parameter, and they think of the algebra, the C-star algebra, sitting as a family above this parameter space, and then they focus on the limit of H bar going to 0. And so they introduce a structure that they call continuous bundle of C-star algebras, but the main idea is basically the same. That we have a family of models over this parameter space. Another well-known example is S duality, in particular tau going to -1 tau. Now you might think, well, if this is our modulus, then this moves us. You might think that this move brings us to a different point in the moduli space, but remember, this moduli space for tau it has some identifications. So actually, these are the same points, only labeled with different coordinates. They are the same point on the moduli space. So this means that this transformation acts vertically on the fibers. It doesn't move us on the moduli space, but it takes us to a different place in the fiber. And likewise for T duality with R going to 1/R. So these dualities move us only vertically from one point in the fiber to another. Okay, so let me illustrate this in the Seiberg-Witten theory, and I will be brief about this in my paper. There's an appendix with extensive details on this. So Seiberg-Witten theory is a fully quantum theory that is the low energy of n equals 2 super Yang-Mills theory. And it is the phase, it is the perturbative phase is the phase where the global symmetry is broken by the Higgs mechanism. The states are the excitations of the U1 gauge field, the Higgs field, and their supersymmetric partners. But in addition, there are non-perturbative solitonic states. For example, states of monopoles, but also dions, so particles that are both electrically and magnetically charged. And of course, part of the interest, I mean, a lot of the interest in the Seiberg-Witten theory was because it gave them a handle on these non-perturbative states. Now, this theory enjoys an SL2Z electric magnetic quasi-duality that relates different states. And it has a moduli space of vacua, which are parameterized by the expectation value of the Higgs field. So I call it U following Seiberg-Witten, which is the trace of phi squared. So phi is the Higgs field. Now, semi-classically, this is simply A squared, where A is the value of the Higgs field itself at the minimum of the potential. However, this relation gets perturbative and non-perturbative corrections. And that's where all the interesting physics of the Seiberg-Witten model is sitting in that relation between U and A. Now, we can characterize, so the states are characterized by the charges, by the electric and magnetic charges. I will here focus more on the quantities, which, as Seiberg and Witten do, which are these pairs of A as a function of U and A dual as a function of U, where A dual is here the Legendre transform of A. Now, these are multivalued sections on the moduli space. They are characterized by monodromy. So this moduli space, which is the complex plane, so it's a complex plane, complex U plane. Seiberg and Witten argued that this complex plane has 3 punctures. And if you go around, if you move around, go in a circle around one of these punctures, you get these quantities get multiplied by a certain factor, a monodromy. And your state acquires a magnetic charge. It gets mapped, for example, if you start with an perturbative electric state, you get, in addition, a magnetic charge. So you map an electric state to a dionic state. So they were able to make statements about these non-perturbative states from these relatively simple considerations of the monodromies of these quantities that they basically got by solving this equation. Now, the physical interpretation is that these non-perturbative states become massless at the singularity. They kind of become, they are above the moduli space. And then if you go around the monodromy, you are basically, a new state appears. You are going from one point in the fiber to another. So the fiber above a point contains different non-perturbative states, and the SL2Z transformation slides us up and down a fiber. What is the interpretation of these new states? They are states that have been integrated out in the Wilsonian effective action. So remember that we started off at low energy, so high energy states have been integrated out. But if you are near a singularity, then there might be states there that near the singularity actually become massless. And so they cannot be neglected. So what this does is it actually takes into account those states that have been initially neglected, that are normally not part of the low energy spectrum if you are far away from such a singularity, but that are now important. Now, there is also a Riemannian metric on the moduli space is defined in this way. So remember that u and u bar are the coordinates on the moduli space. U is a local coordinate on the moduli space. And where does this metric come from? It is basically a volume factor that comes from the Wilsonian effective action of the quantum field theory. So the Wilsonian effective action written here contains a renormalization factor, which comes from quantum effects. So this function f of phi, where phi is the expectation value of the Higgs field, contains an infinite series of renormalization effects. So that's the origin of that metric. So then the way that Seiberg and Witten formulate this in terms of this model bundle is they say, and there is somewhat of an idealization involved here. So it is a holomorphic vector bundle with general fiber C2 isomorphic to C2, and a moduli space, which is the U-punctured plane. There is a local holomorphic section, which I already mentioned here, and the structure group is SL2Z, which is the discrete subgroup of the moduli space metric. So the metric on the complex plane. But now here it would normally be SL2R, but here because of quantum effects, it's broken to a subgroup. Now the point of having these fibers is that the diffeomorphisms are not globally defined. They are only defined on overlapping regions. So we have different formulations of these pairs using different coordinates. So the coordinates have a region of validity. And once we are outside the region of validity, we need to make a change of coordinates. And the fiber bundle structure allows you to precisely do that. So the role of quasi-duality here is that they are given by the transformations required for patching together the fibers of the bundle overlapping open regions on the moduli space. So on the overlaps between two regions, you can change coordinates from, let's say, A and A dual to some other set of coordinates. Okay, as I said, the global properties of the bundle, like the monodromies, the main property here is the monodromy, carries important information about these massless states that emerge unexpectedly in the low energy spectrum. I think. So these are non-perturbative solitonic states. As I said, the metric of the theory comes from the kinetic term in the Wilsonian effective action. So it does change the propagation speeds and energies of your field. So even though it's not a space-time metric in this model, it does influence the propagation of the field simply because your field satisfies a different equation, a modified equation. Now there are unique completions of this theory, as we started from the low energy limit of this n equals 2 theory. One of the ways of doing a UV completion is in string theory realizations. And there, what happens is that this moduli space becomes part of the physical ambient space of a configuration of D branes. There's a configuration of intersecting D branes, and at the intersection you get there's a two-dimensional surface which has a metric that is precisely the Seiberg-Witten metric, and you can think of the Seiberg-Witten theory as the theory on the world volume of these D branes. So that means that this moduli space is part of the ambient space-time, and the metric is part of the space-time metric in that case. So at least in this context, there is a realist interpretation in the sense of, we have a metric and it is actually part of a physical metric in the space-time. So that does bring questions about the relation between moduli space metrics or metrics in theory space and space-time metrics, which in string theory sometimes seem to be somewhat blurred. So to conclude, the geometric view generalizes and assumes the usual semantic view as which we recover as a special case where we have a bundle that is the product of the base and the fiber. It is based on scientific practice, so I don't have a commitment to a preferred mathematical formalism. I didn't look into these bundles because I like them, but just because I think they're useful to look at the examples, and because I think it's something that is missing in the philosophical discussions, and that we could take advantage of by also by including these moduli spaces. So therefore, I have proposed model bundles as structures that incorporate the relation between the models and their moduli spaces. And this also highlights the previously underappreciated role of quasi-duality. So a lot of the philosophical discussion has focused on dualities, but we see that there is also an interesting role to precisely quasi-dualities, where the duality doesn't extend to the whole moduli space. And also that underlines how the inter-theoretic relations can really change our description of physical theories. And so philosophical discussions in the past have often been blind to parameters. There was no preference for defining a theory as having fixed parameters or running parameters that can vary. It was either a matter of philosophical preference or convention. But here we have an argument from physics for taking these parameters seriously as part of our theory, because they actually do some physical work and contain some physical information. So there are a lot of more examples that could be worked out of this geometric view, and I think they also open up some interesting questions, for example, about emergence, and also about the heuristic role for the geometric view in developing quantum field theories and theories of quantum gravity. So here are some references, and I will leave it there. Thank you.
Thank you very much. We now have a couple of minutes for discussion. Hans.
Yeah, thank you very much. So I was wondering whether your model bundle can be applied also to more mundane models, like theories. I don't know how you would call it, GR, you would call it a theory or a model, or even like Lagrangian theories for particles, classical mechanics, or special relativity.
They might, but for me, the essential, I mean, one of the points is this lift up between models and theories. So if we think of GR, let's say as a theory, then yeah, maybe. So I don't see if we have, quasi-duality. So we would need a quasi-duality. So taking GR just by itself, that would be again the old-fashioned case of the limiting case of the usual semantic view. So in that case, I'm not sure there would be a gain in thinking of these terms. So it's mostly in cases where we have examples of these quasi-dualities that we can put. I mean, for example, there's the duality actually between one could ask between general relativity and these Einstein algebras. So in that case, one might ask, or the Newton-Cartan theory, it's not a duality, but it's some form of reduction of theoretical equivalence. So those types of reformulations, those might give interesting. So I think this framework is suitable for those kinds of investigations.
Or teleparallel gravity, for
Yeah,
instance.
Yeah. And so that, I mean, some of those cases are also cases of reduction, where you take a parameter to a limit, and that's also the motivation of both Lanzmann and also Feindsig, where they look at the H bar going to zero limit. So their interest into looking into model bundles is precisely to have a more precise framework to study the H bar going to zero limit. And so yeah, that could be applied to these other cases.
Other questions?
Yeah, maybe point out that more recent developments in the study of cyberwritten theory point out actually that the bundle structure is actually an emergent and perturbative thing. And actually there is no, in the non-perturbative uplifting of cyberwritten theory, there is actually no bundle. There is an entire function of the space, which is the contrary of a bundle. And this is related to quantum mechanical completions of cyberwritten theory. There is a very concrete paper on this by Alba Grassi, who is here in Geneva, who is called Cyberwritten Theory as a Fermi gas, where she shows, based on work that we did before, that the bundle structure might be just in some realizations might be not the last word. So in a sense, the bundle structure might not actually be more like a perturbative mirage than as essential thing. I mean, it's like a little bit. You were doing WKB in quantum mechanics, right? Then you will have all these singularities because, but in actual completions, for example, you should have everything completely smooth. And then you can actually show that the cyberwritten solution, you can actually make it as an approximation to an entire function of moduli space. So a function with no singularities. So all these monopole and diode singularities can eventually be totally washed out in a fully non-perturbative description. So I'm not saying that this is that just pointing out that there are mathematical constructions that in a sense put the bundle structure in a more complicated setting in a sense.
No, thanks for that. I would be very interested to discuss that. In my paper, I discussed some generalizations of the bundle structures. I don't claim that the bundle structure is like the final word. So even here, I mentioned that there are some idealizations already in the cyberwritten case. So even here, there are generalizations that one can visit, but I would be very interested to learn more about that.